the neutral current thus return to the power plant. To elaborate, in a balanced three-phase electrical system, the neutral current is ideally zero. This is because the currents in each of the three phases are equal in magnitude and 120 electrical degrees apart, effectively cancelling each other out at the neutral point. However, real-world electrical systems are rarely perfectly balanced. Imbalances arise from various factors, such as unequal loading on the phases, single-phase loads connected to a three-phase system, and variations in impedance within the electrical distribution network. In an unbalanced system, the currents in the three phases are no longer equal, resulting in a non-zero neutral current. This neutral current flows back to the power plant through the neutral conductor. The neutral conductor provides a low impedance path for the return of unbalanced currents, ensuring that voltage levels remain stable and equipment operates correctly. Now, concerning the issue of stray voltage affecting livestock. Stray voltage is a phenomenon where small electrical potential differences exist between conductive objects that animals may come into contact with. These objects could include water troughs, metal fences, and the ground itself. Stray voltage is typically caused by a combination of factors, including imbalances in the electrical system, poor grounding practices, and inductive coupling from nearby power lines. When an animal comes into contact with two objects at different electrical potentials, a small current may flow through its body, resulting in a mild electric shock. While these shocks are generally not lethal, they can be uncomfortable and stressful for animals, leading to reduced milk production, weight gain, and overall health. Addressing stray voltage involves a multifaceted approach, including improving grounding practices, balancing electrical loads, and shielding against inductive coupling. Firstly, using a properly sized neutral conductor is crucial for minimizing voltage drop and ensuring adequate current carrying capacity. The neutral conductor should be sized according to the National Electrical Code, NEC, or other applicable electrical codes, taking into account the anticipated neutral current load. A properly sized neutral conductor will minimize voltage drop and reduce the potential for stray voltage to develop. Secondly, bonding all electrical equipment to the neutral conductor helps to create a common ground potential, reducing the likelihood of voltage differences between conductive objects. Bonding involves connecting all metal enclosures, conduits, and other non-current carrying metal parts to the neutral conductor, providing a low impedance path for fault currents to flow back to the source. This helps to ensure that any fault currents are quickly cleared, minimizing the risk of electric shock. Thirdly, using ground rods to connect the neutral conductor to the earth provides an additional path for fault currents to flow back to the source, further reducing the risk of electric shock. Ground rods are typically installed at the service entrance and at various points throughout the electrical system, providing a low impedance connection to the earth. This helps to stabilize the neutral potential and reduce the potential for stray voltage to develop. In addition to these measures, there are a number of other steps that can be taken to reduce stray voltage, including balancing electrical loads, using shielded cables, and installing isolation transformers. Balancing electrical loads involves distributing the load evenly across the three phases of the electrical system, reducing the potential for imbalances and neutral current flow. Shielded cables can help to reduce inductive coupling from nearby power lines, minimizing the potential for stray voltage to develop. Isolation transformers can be used to isolate sensitive equipment from the electrical system, further reducing the risk of electric shock. Stray voltage can also arise from various other sources. Inadequate wiring or insulation breakdown in electrical equipment can lead to leakage currents that contribute to stray voltage. Faulty appliances or equipment connected to the electrical system can also introduce stray voltage. Grounding systems that are not properly installed or maintained can result in increased stray voltage levels. External factors, such as nearby power lines or underground cables, can induce stray voltage through electromagnetic induction. Soil conditions, such as moisture content and conductivity, can affect the distribution and intensity of stray voltage. The presence of underground metallic structures, such as pipelines or fences, can also influence stray voltage patterns. Now, delving deeper into the technical aspects, the neutral conductor in an electrical system serves as the return path for current in a single-phase circuit and carries the unbalanced current in a three-phase circuit. It is typically connected to the grounded neutral point at the power source, such as a transformer or generator. The purpose of the neutral conductor is to provide a low impedance path for current to flow back to the source, ensuring that voltage levels remain stable and equipment operates correctly. The size of the neutral conductor is determined by the anticipated neutral current load, as specified in the NEC or other applicable electrical codes. In a balanced three-phase system, the neutral current is ideally zero, but in an unbalanced system, the neutral current can be significant. The neutral conductor must be sized to handle the maximum anticipated neutral current without overheating or causing excessive voltage drop. Grounding, on the other hand, refers to the connection of electrical equipment and systems to the earth. The purpose of grounding is to provide a low impedance path for fault currents to flow back to the source, protecting people and equipment from electric shock. Grounding is typically achieved by connecting a grounding electrode, such as a ground rod or ground plate, to the earth and then connecting all metal enclosures, conduits, and other non-current carrying metal parts to the grounding electrode. The grounding system must be designed and installed in accordance with the NEC or other applicable electrical codes to ensure that it is effective in protecting against electric shock. Bonding is the process of connecting all metal enclosures, conduits, and other non-current carrying metal parts together to create a common ground potential. The purpose of bonding is to reduce the likelihood of voltage differences between conductive objects, minimizing the risk of electric shock. Bonding is typically achieved by using bonding jumpers to connect all metal parts together, creating a continuous electrical path. The bonding system must be designed and installed in accordance with the NEC or other applicable electrical codes to ensure that it is effective in reducing the risk of electric shock. To further clarify the role of the neutral, consider a typical 120 volts alternating current single-phase circuit. This circuit has two wires: a hot wire, which carries the current from the power source to the load, and a neutral wire, which carries the current back from the load to the power source. The hot wire is typically black or red, while the neutral wire is typically white or grey. The neutral wire is connected to the grounded neutral point at the power source, providing a return path for the current. In a properly functioning circuit, the current flowing through the hot wire is equal to the current flowing through the neutral wire. However, if there is a fault in the circuit, such as a short circuit to ground, the current will flow through the grounding system instead of the neutral wire. This will cause the circuit breaker to trip, disconnecting the power to the circuit and preventing electric shock. In a three-phase system, there are three hot wires, each carrying a current that is 120 electrical degrees out of phase with the other two. The neutral wire is connected to the neutral point of the three-phase transformer or generator. In a balanced three-phase system, the currents in the three hot wires are equal in magnitude and 120 electrical degrees apart, so the neutral current is zero. However, in an unbalanced three-phase system, the currents in the three hot wires are not equal, so there is a neutral current. The neutral current flows through the neutral wire back to the power source. It's also helpful to consider the perspective of electrical safety standards and regulations. The NEC, published by the National Fire Protection Association, NFPA, is the primary electrical safety standard in the United States. The NEC provides detailed requirements for the design, installation, and maintenance of electrical systems, including grounding and bonding. Compliance with the NEC is essential for ensuring the safety of electrical systems and protecting people and property from electric shock. Other organizations, such as the Institute of Electrical and Electronics Engineers, IEE, and the International Electrotechnical Commission, IEC, also develop electrical safety standards. These standards provide guidance on various aspects of electrical safety, including grounding, bonding, and protection against stray voltage. Understanding and complying with these standards is crucial for electrical engineers and technicians to ensure the safe and reliable operation of electrical systems. Now let's discuss stray voltage mitigation techniques in more detail. One effective technique is to improve the grounding system. This involves installing additional ground rods, connecting them to the neutral conductor, and ensuring that all metal enclosures and equipment are properly bonded to the grounding system. The grounding system should be designed to provide a low impedance path for fault currents to flow back to the source, minimizing the potential for voltage differences to develop. Another technique is to balance the electrical loads. This involves distributing the load evenly across the three phases of the electrical system, reducing the potential for imbalances and neutral current flow. Balancing the loads can be achieved by carefully planning the connection of electrical equipment to the different phases of the system. Another technique is to use shielded cables. Shielded cables have a metallic shield that surrounds the conductors, which helps to reduce inductive coupling from nearby power lines. The shield is typically grounded, providing a path for induced currents to flow back to the source. Another technique is to install isolation transformers. Isolation transformers are used to isolate sensitive equipment from the electrical system, further reducing the risk of electric shock. Isolation transformers have separate primary and secondary windings, with no direct electrical connection between them. This helps to prevent fault currents from flowing from the primary side to the secondary side, protecting the equipment and personnel connected to the secondary side. Furthermore, regular inspections and maintenance of electrical systems are crucial for preventing stray voltage and ensuring electrical safety. Inspection should include checking the grounding system for corrosion and damage, testing the bonding connections for continuity, and measuring voltage levels at various points in the system. Maintenance should include repairing any damaged or corroded components, tightening loose connections, and replacing any faulty equipment. By implementing these measures, it is possible to significantly reduce the risk of stray voltage and protect animals and people from electric shock. Let's also consider the role of advanced technologies in detecting and mitigating stray voltage. One such technology is the use of advanced metering infrastructure, OMI, which allows for real-time monitoring of voltage and current levels throughout the electrical distribution network. AMI systems can detect voltage imbalances and other anomalies that may indicate the presence of stray voltage. Another technology is the use of ground fault circuit interrupters, GFCIs, which are designed to detect small leakage currents to ground and quickly interrupt the circuit, preventing electric shock. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Another technology is the use of surge protective devices, SPDs, which are designed to protect electrical equipment from voltage surges caused by lightning or other transient events. SPD can help to prevent damage to equipment and reduce the risk of stray voltage caused by voltage surges. It is also important to consider the economic implications of stray voltage. Stray voltage can cause significant economic losses for farmers due to reduced milk production, weight gain, and overall health of livestock. In addition, stray voltage can damage electrical equipment and increase energy costs. By implementing measures to reduce stray voltage, farmers can improve their profitability and reduce their operating costs. In conclusion, the neutral current does indeed return to the power plant, particularly in unbalanced systems. Stray voltage resulting from electrical imbalances can pose a threat to livestock. By implementing appropriate measures, such as proper neutral conductor sizing, bonding, grounding, and regular inspections, it is possible to significantly reduce the risk of stray voltage and ensure electrical safety. These measures not only protect animals and people from electric shock, but also improve the reliability and efficiency of electrical systems. Moreover, the adoption of advanced technologies such as AMI, GFCIs, and SPD can further enhance stray voltage detection and mitigation efforts, leading to safer and more sustainable electrical systems. Remember, electrical safety is a shared responsibility requiring the collaboration of electrical engineers, technicians, farmers, and other stakeholders to ensure the safe and reliable operation of electrical systems. By working together, we can create a safer and more sustainable future for all.